Gamma-ray burst obliteration. One day, without warning, the sky lights up brighter than a billion suns. A gamma-ray burst from a dying star thousands of light-years away has just bathed Earth in lethal radiation. This is one of the most violent events in the universe, and if it happens close enough and aims directly at us, we're done. No time to prepare, no time to hide. Just instant, catastrophic destruction of the ozone layer followed by mass extinction. The burst itself lasts only seconds, but those seconds release more energy than our sun will produce in its entire lifetime. The radiation tears through our atmosphere, shredding the ozone layer that protects us from solar radiation. Within hours, the sky becomes a death sentence. UV radiation floods the planet at levels nothing evolved to handle. Plants begin to die. The food chain collapses from the bottom up, but it gets worse. The radiation doesn't just burn, it chemically transforms our atmosphere. Nitrogen and oxygen combine into nitrogen dioxide, turning the sky brown and blocking sunlight. The planet plunges into an ice age while simultaneously being cooked by radiation. Anything that survives the initial blast faces starvation in the dark, frozen wasteland that follows. And here's the terrifying part: we wouldn't see it coming. Gamma-ray bursts travel at the speed of light. The deadly radiation arrives at the same moment we'd see the burst happen. No warning, no preparation, just sudden annihilation. Scientists estimate a gamma-ray burst within 6,000 light-years could cause mass extinction. There are several candidates in our cosmic neighborhood. Some are closer than we'd like. The odds of it happening in our lifetime are low, but they're not zero. And if it happens, there's nothing we can do. No bunker goes deep enough. No shelter blocks that kind of radiation. We've built our entire civilization on a planet that sits in a cosmic shooting gallery, and gamma-ray bursts are the bullets we'll never see coming. Rogue black hole encounter. Black holes don't stay put. They move through space, and some wander alone, invisible and deadly. If a rogue black hole passed through our solar system, it wouldn't need to hit Earth to destroy us. Its gravity would tear apart the delicate orbital mechanics that keep our planet stable, flinging us into space or into the sun. Either way, we're extinct. These stellar corpses are invisible until they're eating something. No light escapes them, which means a rogue black hole could be heading toward us right now, and we wouldn't know until it was close enough for its gravity to start affecting planets. By then, it's too late. The chaos begins long before any collision. As the black hole approaches, its gravity distorts the orbits of outer planets first. Jupiter and Saturn would be yanked from their paths, their protective influence over Earth gone. Asteroids and comets, usually kept in check by Jupiter's gravity, would rain down on the inner solar system in unprecedented numbers. Earth would face bombardment like nothing in recorded history. Then the black hole's gravity reaches us directly. Tides become catastrophic as the black hole pulls on Earth's water and even the planet itself. Earthquakes of unimaginable magnitude crack the crust. Volcanic eruptions explode across the globe. The atmosphere tears away, stripped by gravitational forces. If we're lucky, this kills us quickly. If we're unlucky, the black hole's gravity slingshots Earth out of the habitable zone, either into deep space or toward the sun. Thrown into space, Earth becomes a rogue planet. The sun disappears. Temperatures plummet to near absolute zero. The oceans freeze solid. The atmosphere freezes and falls as snow. Any survivors huddled in underground bunkers with nuclear reactors might last weeks or months, but eventually, everyone freezes or starves. Thrown toward the sun, Earth heats rapidly. The oceans boil. The atmosphere burns away. The surface becomes molten. No one survives either scenario. And the worst part is, we might never see it coming. Detecting rogue black holes is nearly impossible. They're dark, silent, and small relative to cosmic distances. One could be heading toward us right now, and our first indication would be when Saturn suddenly shifts its orbit. By then, we'd have maybe months to realize we're watching our extinction in slow motion. Asteroid impact apocalypse. An asteroid large enough to end civilization doesn't have to be planet-sized. A rock just 10 kilometers across, about the size of a small city, hitting at typical cosmic speeds carries the energy of 1 billion nuclear bombs. We know this can happen because it already has. The dinosaurs learned this lesson 65 million years ago when an asteroid ended their reign. We're next in line if we're not careful. The immediate impact zone becomes hell on Earth. Everything within hundreds of kilometers vaporizes instantly. The shock wave levels everything within thousands of kilometers. But the real extinction event comes from what happens next. The impact throws trillions of tons of vaporized rock, dust, and debris into the atmosphere. This material spreads across the globe, blocking out the sun. Temperatures plummet. Photosynthesis stops. Plants die within weeks. Herbivores starve. Carnivores run out of prey. The food chain collapses ecosystem by ecosystem. Humans might survive the initial impact if we're far enough away. We might even survive the first year in the dark, eating stored food and whatever we can grow artificially. But we can't outlast the decade of darkness that follows. Crops fail globally. Stored food runs out. Billions starve. The survivors turn on each other fighting over the last resources. Civilization collapses into barbarism, and barbarism collapses into extinction. We've cataloged most of the large asteroids that could end us, and none are currently on collision courses. That's the good news. The bad news is we haven't found everything. Smaller asteroids, still large enough to cause devastation, could appear with little warning. And comets from the outer solar system can arrive on trajectories we never saw coming, giving us months or weeks to prepare for an extinction we can't prevent. We've started developing planetary defense systems, spacecraft that could deflect an asteroid given enough warning, nuclear weapons designed to push threatening rocks off course. But these systems are theoretical, underfunded, and untested against real threats. If a large asteroid appeared tomorrow on a collision course, we'd probably just watch it come, knowing we're about to join the dinosaurs in extinction. The universe doesn't care about our survival. Rocks fly through space randomly. One of them has our name on it. We just don't know when it arrives. Solar superstorm catastrophe. The sun isn't stable. It has moods. And when it gets angry, it throws tantrums that could end technological civilization and, by extension, end us. A solar superstorm, a massive ejection of charged particles and radiation, could fry every electrical system on Earth. No power, no communication, no transportation, no food distribution, billions dead within months. Not from the storm itself, but from the collapse that follows. We know solar superstorms can happen because they have. The Carrington event in 1859 was a solar storm that hit Earth when our technology consisted of telegraph wires. Those wires melted. Telegraph operators received electric shocks. Auroras appeared as far south as the Caribbean. If that storm hit today, the damage would be catastrophic beyond comprehension. Modern civilization runs on electricity. Every system we depend on needs it. When a solar superstorm strikes, the first casualty is the power grid. Transformers overload and explode. Power plants shut down. The electrical backbone of civilization melts in hours. And it doesn't come back quickly. The specialized equipment needed to repair power grids takes months to manufacture even in ideal conditions. With no power, we can't manufacture anything. No power means no water pumping. Cities run out of clean water within days. No power means no refrigeration. Food spoils. Supply chains collapse. Grocery stores empty within a week. No power means no fuel pumps. Even if you have a car and gasoline exists, you can't pump it without electricity. Transportation stops. No power means no communication. Cell towers die. Internet vanishes. You can't call for help. You can't coordinate with others. You're isolated in the darkness, surrounded by millions of equally desperate people. The cities become death traps first. Millions packed into small areas with no food, no water, no sanitation. Disease spreads. Violence erupts as people fight over dwindling resources. The smart ones flee to rural areas, but rural areas can't support sudden population influxes. Farming communities become fortresses. Outsiders are turned away, or worse. Within months, billions have starved or killed each other. The survivors face a world thrown back to pre-industrial conditions, but without the knowledge or infrastructure to sustain even that level of civilization. We lost those skills generations ago. Most people don't know how to grow food, purify water, or survive without modern technology. And even if the sun doesn't hit us with a superstorm, it will eventually die. In about 5 billion years, the sun will expand into a red giant, swallowing Earth entirely. That's too far in the future to worry about, except it reminds us that our star isn't permanent. It has an expiration date, and long before it dies, it will become unstable, making Earth uninhabitable. The sun gives us life, but the sun can also take it away with a single angry outburst we won't see coming until it's already here, traveling at the speed of light, ready to plunge us into darkness and extinction. Supernova shockwave. If a star goes supernova too close to Earth, the explosion releases so much energy it makes gamma-ray bursts look gentle. The shockwave alone, traveling through space at thousands of kilometers per second, would strip away our atmosphere and sterilize the surface. Even at a distance of 30 light-years, a supernova could trigger mass extinction. Several candidate stars sit within that danger zone. When a massive star exhausts its nuclear fuel, it doesn't fade away quietly. It explodes with violence that briefly outshines entire galaxies. The core collapses in fractions of a second, rebounding in a catastrophic detonation that blasts the star's outer layers into space at relativistic speeds. If this happens close enough to us, we're in the path of that destruction. The first wave to hit us would be light and radiation. The sky would light up with a new star brighter than the full moon, visible even during daytime. This would be beautiful for about the same amount of time it takes to die from radiation poisoning. The high-energy radiation tears through our atmosphere, destroying the ozone layer and allowing lethal solar and cosmic radiation to reach the surface. Then comes the particle wave. Charged particles from the explosion, accelerated to near light speed, slam into Earth's atmosphere and surface. These cosmic rays damage DNA, cause cancers, kill cells outright. Nothing on the surface survives prolonged exposure. Plants die, animals die, humans die. The oceans might provide temporary shelter, but even deep water can't block all the radiation. Finally, the physical shockwave arrives. Not air, because space is a vacuum, but the expanding shell of gas and dust from the exploded star. When this wall of stellar debris hits Earth, it compresses and heats our atmosphere, potentially stripping it away entirely or at minimum making it toxic and unbreathable. The good news is, no stars close enough to threaten us are currently at risk of going supernova in the near future. The bad news is our understanding of stellar evolution isn't perfect. A star we think is stable might surprise us. And on cosmic timescales, near future could mean thousands of years or tomorrow. We wouldn't know until it happened. If a nearby star goes supernova, our warning would be the light reaching us, meaning the deadly radiation arrived simultaneously. We'd have no time to prepare, no time to hide, just time enough to look up at the beautiful new star in the sky and realize we're looking at our extinction. Planetary collision chaos. Our solar system looks stable, but that's an illusion. Planetary orbits are chaotic systems. Given enough time, gravitational interactions between planets could spiral out of control, resulting in planetary collisions or ejections. If Earth collided with another planet or was thrown out of its orbit, extinction would be instant and absolute. The chaos is already happening, just slowly. Planets tug on each other gravitationally with every orbit. These tiny perturbations accumulate over millions of years. Computer simulations show that, given billions of years, there's a small but real chance Mercury could be ejected from the solar system or thrown into a collision course with Venus or Earth. If Mercury hit Earth, the result would make asteroid impacts look like gentle taps. The collision would vaporize both planets' surfaces. The energy released would liquefy rock. The combined mass would briefly form a molten sphere of death where two planets used to be. Nothing survives. No bunker goes deep enough. No preparation matters. The planets merge into a new, larger planet that takes millions of years to cool, and by then, Every trace of life that existed on either world has been erased. But collision isn't the only danger. Gravitational interactions could also eject Earth from the solar system entirely without any impact. A series of close passes with other planets could transfer enough momentum to throw Earth out of its orbit, sending us into deep space as a rogue planet. At first, this might seem survivable. Earth wouldn't instantly freeze. The core would keep generating heat for millions of years. But without the sun, photosynthesis stops immediately. Plants die within weeks. The food chain collapses. Temperatures plummet as the sun shrinks to just another star in the sky. Within a year, the surface is frozen solid. The atmosphere begins to condense and fall as snow. The oceans freeze from the top down, eventually becoming solid ice kilometers thick. Any humans still alive would be huddled around nuclear reactors or geothermal vents, the last heat sources on a dead world hurtling through the void. They might survive months or even years, but eventually the fuel runs out, the heat dissipates, and the last humans freeze to death in absolute darkness, trillions of kilometers from the sun that used to give us life. The probability of this happening in the near future is essentially zero, but over hundreds of millions of years, the odds climb. Eventually, if nothing else kills us first, the chaotic dance of planets might throw us into extinction simply because orbital mechanics are fundamentally unstable over long enough timescales. Cosmic void transition. Space itself might not be stable. Some physicists worry that the universe exists in a false vacuum state, a temporary condition that could suddenly transition to a lower energy state. If this happened, a bubble of true vacuum would expand at the speed of light, rewriting the laws of physics as it goes. Inside the bubble, atoms wouldn't hold together. Matter as we know it couldn't exist. Earth would simply cease to be. The terrifying part about vacuum decay is we'd never see it coming. The bubble expands at light speed, meaning the destruction arrives at the same instant we'd see it. No warning, no preparation, just instant obliteration as the fundamental forces holding our atoms together suddenly change. You wouldn't feel pain. You wouldn't have time to feel anything. One moment you exist. The next moment, the bubble reaches you, and you stop existing along with everything else. The atoms that made up your body disperse into whatever exotic particles are stable in the new vacuum state. Some physicists argue this can't happen, that our universe is already in the lowest energy state. Others aren't so sure. The discovery of the Higgs boson raised unsettling questions about vacuum stability. Calculations suggest we might be in a metastable state, stable for now but vulnerable to triggering into true vacuum if enough energy concentrates in one spot. High-energy particle collisions, whether natural or from our accelerators, might be able to nucleate the transition. If we're unlucky, we could trigger our own extinction just by doing physics experiments. But even if we're careful, cosmic rays bombard Earth constantly with energies far higher than any accelerator we've built. If vacuum decay is possible, it probably would have been triggered already by natural processes. The fact that we still exist suggests either vacuum decay isn't possible or we've been extraordinarily lucky. That luck won't last forever. If vacuum decay is possible, it will eventually happen somewhere in the universe. Maybe in a galaxy far away, maybe right next to us. And once it starts, it never stops. The bubble keeps expanding forever, destroying everything in its path, remaking the universe into something where stars, planets, and life cannot exist. We wouldn't even leave ruins. There'd be no evidence we ever existed because the atoms that made up our world would be transformed into something unrecognizable. Our entire legacy would be erased in an instant by a wall of physics we can't see, can't stop, and won't survive. Magnetar radiation pulse. Magnetars are neutron stars with magnetic fields so powerful they distort reality itself. If a magnetar released a giant flare aimed at Earth, even from thousands of light years away, the radiation could strip our atmosphere and fry the surface. These stellar corpses are rare, but they exist in our galaxy, and they're unpredictable. When they flare, they release energy in seconds that our sun takes thousands of years to produce. A magnetar is what you get when a massive star collapses into a sphere only 20 kilometers across, but containing more mass than the Sun. The gravitational pressure is so intense that protons and electrons merge into neutrons, creating a giant atomic nucleus held together by gravity. The magnetic field is 1,000,000,000,000 times stronger than Earth's. Strong enough to rip iron from your blood if you got close enough, though you'd never survive long enough for that to matter. Magnetars occasionally suffer starquakes. The solid neutron crust shifts suddenly, releasing enormous amounts of magnetic energy as a giant flare. These flares emit more energy in 1/10 of a second than our Sun produces in 100,000 years. If one of these flares hit Earth, the high-energy radiation would ionize the atmosphere, destroy the ozone layer, and sterilize the surface with radiation levels nothing could survive. The recorded magnetar flare in our galaxy happened in 2004 from a magnetar called Skira 1806-20. It was 40,000 light-years away, and the radiation still disrupted Earth's ionosphere and blinded several satellites. If that flare had come from a magnetar just 10,000 light-years away, the effects would have been catastrophic. And there are magnetars closer than that. We know of about 30 magnetars in our galaxy, but there are probably more we haven't detected. They're small, distant, and dark, except when they flare. One could be relatively close, and we won't know until it decides to have a starquake aimed in our direction. Then we'd have about the same warning time as a gamma-ray burst, which is to say, none at all. The radiation travels at light speed. We see it and die from it simultaneously. No time to hide. No shelter adequate. Just sudden death from a stellar corpse thousands of light-years away having a bad day. The universe is full of ways to kill us, and magnetars are one of the more exotic and terrifying options. A star so dense and magnetic that its tantrums can sterilize worlds across thousands of light-years, and we just have to hope none of them point their bad days in our direction. KUGELBLITZ formation. A KUGELBLITZ is a black hole formed not from matter but from pure energy concentrated in a small enough space. If enough electromagnetic radiation concentrated in one spot, it could collapse into a black hole. This is theoretical but not impossible. High-energy cosmic events might create micro-KUGELBLITZes. If one formed near Earth or in our solar system, its gravity would be just as deadly as any stellar black hole, despite potentially being microscopic. The concept sounds like science fiction, but it emerges from Einstein's equations. Energy and mass are equivalent. Concentrate enough energy in a small enough volume, and it will collapse under its own gravity, forming an event horizon. This has never been observed, but that doesn't mean it can't happen. Certain high-energy cosmic events might create the conditions. A KUGELBLITZ black hole would be tiny, possibly microscopic, but its gravity would still be real. If one formed inside Earth, it would sink to the core and begin consuming matter. Unlike larger black holes that swallow matter quickly, a micro-black hole would feed slowly, taking thousands or millions of years to consume significant mass. But during that time, its gravity would disrupt Earth's core, affecting our magnetic field, causing earthquakes, destabilizing the planet geologically. Eventually, it would consume enough mass to accelerate the process. Earth would collapse into the growing black hole over centuries or millennia, a slow-motion apocalypse as the ground literally falls into a growing void at the center of our planet. If a KUGELBLITZ formed outside Earth but in the solar system, it might be more immediately dangerous. Its gravity would perturb planetary orbits. Depending on where it formed and its mass, it could destabilize Earth's orbit, throwing us out of the habitable zone. Or it could attract asteroids and comets, sending them raining down on the inner solar system in unprecedented numbers. The probability of this happening naturally is extremely low. KUGELBLITZes, if they can form at all, probably require conditions that don't exist in modern star systems. But the universe is vast and old. Unlikely events happen somewhere. And if advanced civilizations exist, they might be able to create KUGELBLITZes deliberately as weapons or energy sources. We wouldn't know until one appeared, warping space around it, an invisible predator made of bent space-time hungry for anything that falls into its gravity well. Black holes are terrifying enough when they're stellar corpses we can see coming. Black holes made of pure energy, potentially microscopic and impossible to detect until they're already consuming you, are nightmare fuel that might be physically possible. Just another way the universe has found to kill anything unlucky enough to be in the wrong place when one forms. Dark matter catastrophe. We know dark matter exists because we can see its gravitational effects, but we don't know what it is. If dark matter interacts with normal matter in ways we don't yet understand, concentrated dark matter could pose extinction threats. A dense dark matter object passing through the solar system could gravitationally disrupt planetary orbits. Or, if dark matter particles can accumulate in planetary cores, they might trigger processes that destabilize Earth from within. Dark matter makes up 85% of the universe's matter, but we can't see it, touch it, or detect it except through gravity. It doesn't interact with light. It doesn't interact with normal matter except gravitationally, as far as we know. But that, as far as we know, is doing heavy lifting. Our understanding of dark matter is embarrassingly incomplete. We named it dark matter because we have no idea what it actually is. If dark matter has properties we haven't discovered, those properties could be deadly. Some theories suggest dark matter might not be completely non-interacting. Certain models propose rare interactions with normal matter. If those interactions become relevant under specific conditions, dark matter could pose threats we haven't imagined. A dark matter asteroid, if such things exist, could pass through Earth undetected until its gravity started affecting things. We'd have no way to see it coming and no way to deflect it. Another theory suggests dark matter might accumulate in stellar cores and planetary cores over billions of years. If enough dark matter collects in Earth's core, it might eventually collapse into a black hole or trigger other exotic processes that destabilize the planet. The core could become gravitationally unstable. Earthquakes and volcanic eruptions could intensify as dark matter interactions heat the core beyond normal levels. Over millennia, Earth could become geologically chaotic, potentially uninhabitable. The terrifying aspect of dark matter threats is our ignorance. We don't know what dark matter is made of. We don't know all the ways it might interact with normal matter. We don't know if there are dark matter structures out there, dark matter planets or asteroids or clouds that could threaten us. We're flying blind through a universe where most of the matter is invisible to us. We've mapped the visible matter, cataloged threats we can see. But dark matter remains a mystery, and mysteries can kill you. If dark matter poses threats, we won't know until something happens. We won't see it coming. We won't understand what's happening. We'll just suddenly face extinction from a threat that's invisible, undetectable, and impossible to fight because we don't understand the physics. The universe might be full of dark matter dangers we can't even conceptualize yet, and we won't know until one of them kills us, teaching us the final lesson about the dark matter that surrounds us, permeates us, and might eventually destroy us without us ever understanding what hit us. Hypernova annihilation. A hypernova is a supernova on steroids, the death explosion of the universe's most massive stars. These explosions release energy that makes ordinary supernovae look weak. If a hypernova occurred close enough to Earth, within a few thousand light years, the radiation and particle emissions would sterilize our planet completely. The gamma rays alone could destroy the ozone layer and cook the surface. Nothing survives. Hypernovae are rare because they require stars at least 40 times more massive than our Sun. These stellar giants live fast and die violently. When they exhaust their nuclear fuel, the core doesn't just collapse. It collapses so catastrophically that it forms a black hole or magnetar immediately. The outer layers don't just explode, they're blown off at relativistic speeds, carrying energy equivalent to our Sun's entire lifetime output released in seconds. The death of these stars is visible across the universe. If one went off in our galaxy, even thousands of light years away, it would briefly be the brightest object in the sky besides the Sun. This would be spectacular for the few hours before the radiation killed everything. The gamma rays would arrive first, traveling at light speed. They'd strip away the ozone layer, allowing solar UV radiation to burn the surface. The high-energy photons would damage DNA in every organism exposed to them. Plants would die. Animals would develop cancers and die within weeks. Humans would face the same fate. burns, radiation sickness, cancers, death. Then the particle wave would arrive, cosmic rays accelerated to near light speed. These would bombard Earth for years, making the surface uninhabitable. Even underground shelters would offer limited protection. The radiation would penetrate deep, contaminating everything, making long-term survival impossible. The expanding shell of stellar debris would take longer to arrive, maybe thousands of years, but when it did, it would compress and potentially strip away what's left of our atmosphere. By then, hopefully, anything that survived would already be dead, because living on a irradiated wasteland for thousands of years waiting for the final blow sounds worse than quick extinction. We know of several hypernova candidates in our galaxy, stars massive enough and close enough to threaten us if they exploded. Eta Carinae is one of the most famous, an unstable monster star about 7,500 light-years away. It's already shown signs of instability. It could go hypernova tomorrow or in 1,000,000 years. We don't know. When it does, we'll find out if 7,500 light-years is far enough to be safe. Early estimates suggest we're right on the edge of the danger zone. If Eta Carinae's gamma-ray burst aims at us, we might face mass extinction. If it aims somewhere else, we might just see a beautiful new star and get a harsh radiation dose but survive as a species. We won't know until it happens. And there might be other hypernova candidates we haven't identified yet, closer stars that could explode without warning. The universe doesn't send save dates for extinction events. We just have to live with the knowledge that somewhere in our galaxy, multiple stars are ticking time bombs, and if one goes off aimed at us, that's it. No second chances. Just sudden death from a star that died thousands of years ago, its light just now reaching us to deliver the final message, you're extinct. Interstellar cloud encounter. Our solar system moves through the galaxy at over 200 kilometers per second. Most of space is empty, but it's not completely empty. Vast clouds of gas and dust drift between the stars. If Earth passed through a dense interstellar cloud, it could have catastrophic consequences. The cloud could block sunlight, plunging us into darkness. It could compress our atmosphere or interact with it chemically. It could even carry radiation or charged particles that strip away our protective layers. Right now, our solar system sits in a relatively empty region called the local bubble, a cavity carved out by ancient supernova explosions. But we won't stay here forever. In a few thousand years, we'll enter the G-cloud, a denser region of interstellar space. The effects are unpredictable, but potentially devastating. As Earth enters a dense cloud, the first effect would be increased drag on our atmosphere. The outer atmosphere would interact with the cloud's gas, heating up and potentially being stripped away. Our protective layers would thin, allowing more cosmic radiation to reach the surface. This alone could cause ecological disruption and increase cancer rates. If the cloud is dense enough, it could block significant sunlight. Temperatures would drop, photosynthesis would decrease, plants would struggle, the food chain would face stress from the bottom up. A prolonged passage through a thick cloud could trigger an ice age as the planet cools from reduced solar input. Some interstellar clouds contain complex organic molecules and even simple amino acids. If Earth passed through such a cloud, it could introduce alien biochemistry to our planet. This might sound like panspermia, the theory that life spreads through space, but it could also introduce incompatible or toxic chemistry. Alien organic compounds could poison ecosystems adapted to Earth's specific biochemistry. The scariest possibility is if the cloud contains radioactive material from previous supernova explosions. Interstellar space is seeded with heavy elements created in stellar explosions. A cloud contaminated with radioactive isotopes could bathe Earth in radiation for thousands of years as we pass through it. The exposure would be gradual but relentless, accumulating in the environment, in the food chain, in our bodies. Cancer rates would skyrocket. Mutations would increase. Over generations, the genetic damage could threaten our species' viability. We can see interstellar clouds with telescopes. We know roughly where they are. But predicting exactly when we'll intersect with them and what the effects will be is difficult. Space moves in 3 dimensions. Clouds drift and change, And our models of galactic motion aren't perfect. We might pass through clouds we didn't predict, or we might narrowly miss clouds we thought we'd hit, and there's nothing we can do about it. We can't change the solar system's course through the galaxy. We're passengers on a planet orbiting a star that's moving through space on a trajectory we don't control. If that trajectory takes us through a deadly cloud, we just have to endure it and hope we survive. Most interstellar clouds are probably harmless, too diffuse to affect us significantly. But dense clouds, radioactive clouds, or prolonged passages could threaten civilization or even our species. It's another cosmic Russian roulette we're forced to play just by existing in a universe where space isn't as empty as it seems. Strange matter conversion. Strange matter is a hypothetical form of matter more stable than normal matter. If it exists, and if it touches normal matter, it could convert that matter into more strange matter in a chain reaction. One strange matter particle, a strangelet, touching Earth could convert the entire planet into a strange matter ball in seconds. This is theoretical, but if it's possible, it's an extinction threat from a single particle we couldn't see coming. Normal matter is made of protons and neutrons, which are made of up quarks and down quarks. Strange matter would be made of up, down, and strange quarks in roughly equal proportions. Theory suggests this configuration might be more stable than normal matter. If that's true, then a chunk of strange matter touching normal matter would be like a crystallization seed. The normal matter would rearrange into the more stable strange matter configuration, releasing energy in the process and continuing the conversion. The chain reaction would be unstoppable. Once started, it would consume the entire planet at a significant fraction of the speed of light. You wouldn't have time to realize what's happening. One moment, Earth exists. Seconds or minutes later, it's a ball of strange matter, slightly smaller and denser than before, with everyone and everything converted into exotic particles. No survivors, no ruins. Just a strange planet where a living world used to be. Strange matter might exist in the cores of neutron stars, compressed into existence by the intense pressures there. If a neutron star collision or similar event ejected chunks of strange matter into space, those strangelets would drift through the galaxy as invisible extinction threats. They'd be small, maybe microscopic, moving at high speeds, impossible to detect until they hit something. If a strangelet hit Earth, we'd have no warning. It would pass through the atmosphere, probably without anyone noticing, hit the surface or ocean, and begin the conversion. Within seconds, the conversion wave would spread from the impact point. The planet would start transforming from the inside out. Anyone at the initial impact site would be converted first. Then the conversion would spread outward at relativistic speeds. Within minutes, the entire planet would be strange matter. The good news is, this is all theoretical. We don't know if strange matter is actually more stable than normal matter. We don't know if strangelets can exist or if they'd really cause conversion chain reactions. The physics is uncertain enough that most scientists aren't losing sleep over strange matter threats. The bad news is, we don't know enough to be certain it's not a threat. If strange matter conversion is possible, the first time we'd find out is when it happens. And if it happens, there's no stopping it, no defense, no escape. Just instant conversion of everything we know into something alien and lifeless. Another theoretical extinction threat from exotic physics we barely understand, lurking in the gaps of our knowledge, waiting to maybe kill us if the universe works in ways we haven't figured out yet. Relativistic kill vehicle. This one isn't natural, but it's a space-based extinction threat worth mentioning. An advanced civilization could accelerate a projectile to relativistic speeds, a significant fraction of light speed, and aim it at Earth. At those velocities, even a small object carries absurd kinetic energy. A relativistic kill vehicle the size of a car hitting Earth would release energy equivalent to multiple nuclear arsenals. The impact would be extinction level, and we'd have almost no warning. The terrifying physics of relativistic projectiles is simple. Kinetic energy increases with the square of velocity. Double the speed, quadruple the energy. At 10% of light speed, a 1-ton projectile carries the energy of several large nuclear bombs. At 90% of light speed, that same projectile carries energy equivalent to thousands of nuclear weapons. The faster it goes, the more unstoppable it becomes. At relativistic speeds, there's no defense. You can't shoot it down. Any weapon you fire at it would hit with closing velocity so high that both the weapon and the target would vaporize, but the target's momentum would continue essentially unaffected. You can't deflect it. The energies involved are too large. You can't evacuate. There's nowhere to go on Earth that would be safe from an impact that powerful. The detection problem makes it worse. A relativistic projectile is small and dark. It doesn't emit light. It's traveling so fast that by the time you see it, maybe by reflected starlight or as it compresses gas in the upper atmosphere, it's already hitting. You'd have seconds at most between detection and impact, not enough time to do anything except realize you're about to die. If an alien civilization wanted to sterilize Earth, a relativistic kill vehicle would be effective, efficient, and almost impossible to defend against. They could launch it from light years away. It would take decades or centuries to arrive, but once launched, it's coming, and there's nothing we could do to stop it. We wouldn't even know who fired it until after the impact, if we survived to analyze the trajectory. This seems like paranoid science fiction, but the physics is real. Accelerating objects to relativistic speeds is just engineering, difficult engineering, but not impossible. Any civilization that achieves interstellar travel would have the technology to create relativistic kill vehicles. Whether they'd use them against us depends on alien psychology we can't predict. The dark forest theory suggests the universe might be full of civilizations hiding from each other, because any civilization that reveals itself risks being destroyed by others using weapons exactly like this. If that theory is correct, we're constantly at risk of relativistic projectiles from civilizations that decided to destroy potential threats preemptively. We wouldn't know they existed until their projectile arrived, traveling at a fraction of light speed, carrying enough kinetic energy to crack continents and boil oceans. We'd die not even knowing who killed us or why. Just another dead world in a galaxy that might be full of them, all killed by the same logical conclusion. In a dark forest where revealing yourself is fatal, shoot first and don't wait to see if the other guy is friendly. It's extinction by game theory, and the game started before we even knew we were playing. Cosmic string collision. Cosmic strings are hypothetical, one-dimensional topological defects in space-time, remnants from the early universe. If they exist, they'd be incredibly thin but infinitely long, with immense gravitational effects. A cosmic string passing through our solar system could gravitationally disrupt planetary orbits or slice through Earth like a wire through cheese, except the wire is a defect in space-time itself, and the cheese is our planet. We wouldn't survive either scenario. Cosmic strings would have formed in the first moments after the Big Bang, when the universe was cooling and symmetries were breaking. They'd be thinner than an atom, but contain mass equivalent to millions of stars per centimeter of length. Their gravity would be intense and weird, not pulling inward like a sphere, but pulling perpendicular to the string's length. If a cosmic string passed near Earth, its gravity would pull on us sideways. Depending on how close it passed, this could be a gentle tug or a catastrophic disruption. A close pass might perturb Earth's orbit, throwing us out of the habitable zone. A very close pass might tidally tear the planet apart as the strange gravitational geometry rips Earth's structure. If a cosmic string actually intersected Earth, it would slice through like we're not even there. The string is a defect in space-time itself. Matter can't resist it. It would cut a line through the planet at whatever angle it approached from. The two halves of Earth would separate. The atmosphere would explosively decompress into space. The cores would be exposed. Both halves would become uninhabitable immediately. If humans survived the initial cut, maybe being on the half that retained some atmosphere temporarily, they'd die within hours as the halves drifted apart and conditions deteriorated. Cosmic strings, if they exist, would be moving at significant fractions of light speed, whipping through space at relativistic velocities. We'd have minimal warning. Maybe gravitational effects would be detected shortly before the string arrived, giving us hours or doomed. Maybe not. Maybe the first sign would be the planet being cut in half. Fortunately, cosmic strings are purely theoretical. We've never detected one. We don't know if they exist at all. Theories that predict them are speculative, but they're consistent with some models of the early universe. If cosmic strings do exist, they'd be rare, which is why we haven't seen one. But rare doesn't mean impossible. The universe is vast and old. Rare events happen. If cosmic strings are real, and one happens to pass through our solar system, it would be an extinction event from a cosmological relic billions of years old. A scar in space-time itself from the birth of the universe, finally intersecting with our planet billions of years later to casually end everything we've ever known. Just bad luck and bad timing, killed by the universe's oldest wounds. Quasar reactivation? The supermassive black hole at the center of our galaxy is currently quiet, dormant, not actively feeding. But it wasn't always quiet. Billions of years ago, it was likely an active quasar, blasting radiation and jets of matter across the galaxy. If it reactivated, if enough matter fell into it to restart quasar-level activity, the radiation could sterilize large portions of the galaxy, including Earth. We'd be fried by our own galactic core. Quasars are the brightest objects in the universe, supermassive black holes actively consuming matter and converting it to energy with terrifying efficiency. The matter falling into the black hole forms an accretion disk that heats to millions of degrees, blasting out radiation across the electromagnetic spectrum. Jets of charged particles stream from the poles at near light speed, extending for thousands of light years. When our galaxy's black hole was a quasar, it would have been visible from across the universe. Now it's dark, quiet, because it ran out of nearby matter to consume. But black holes never truly die, they just wait. If a large gas cloud or a star wandered too close to our galactic core, the black hole would devour it. Enough matter falling in could restart quasar activity. Suddenly, the core of our galaxy would light up with radiation that would make the sun look dim. The radiation would spread outward at the speed of light. Earth is about 26,000 light-years from the galactic center. That means if the quasar turned on today, we wouldn't know for 26,000 years. But when the light reached us, so would the radiation. High-energy X-rays and gamma rays would bombard Earth, destroying the ozone layer, irradiating the surface, killing most life. The radiation would continue for however long the quasar phase lasted, potentially millions of years. If the jets happened to align with Earth, we'd be hit with focused beams of the most energetic particles in the galaxy. Nothing would survive that. The planet would be sterilized, the surface scoured clean by radiation, the atmosphere stripped away. Earth would become a dead rock orbiting a star in a galaxy with an active, deadly core. The likelihood of the galactic core reactivating in a human timescale is very low. Black holes don't just randomly reactivate, they need fuel. The space around our galactic core is relatively empty now. There's no large gas cloud about to fall in. No star is currently on a collision course. We're probably safe for millions or billions of years. Probably. But galaxies collide. When the Milky Way eventually collides with Andromeda in about 4 billion years, the collision will disrupt galactic structures. Gas clouds will be thrown around. Stars will be scattered. Some of that matter will fall into the galactic cores of both galaxies, potentially reactivating them into quasars simultaneously. If humans still exist then, we'll face extinction from the collision fallout, potentially including our own galactic core turning into a deadly radiation source. It's a distant threat, so far in the future it seems irrelevant. But it's a reminder that even our galaxy's heart, currently quiet and safe, could someday wake up and kill us all with radiation from the center of our own cosmic home. Vacuum metastability event. The Higgs field, which gives particles mass, might exist in a metastable state. If it's not in the lowest possible energy state, a quantum fluctuation could trigger a phase transition. A bubble of true vacuum would form and expand at light speed, rewriting fundamental physics as it goes. Inside the bubble, particles might not have mass anymore, or they might have different masses. Either way, atoms wouldn't work the same. Chemistry would break. Matter as we know it would disintegrate. We'd never see it coming. The Higgs field permeates all of space, giving mass to fundamental particles through its interactions with them. When the Higgs field was discovered, physicists calculated its properties and found something unsettling. The field might not be in its lowest energy state. It might be in a local minimum, a temporary stable state that could transition to a lower energy state if disturbed. This is called vacuum metastability. If the Higgs field is metastable, a quantum fluctuation somewhere in the universe could trigger a transition to the true vacuum state. This would create a bubble where physics works differently. The bubble would expand at the speed of light, consuming everything in its path. The edge of the bubble is where the transition happens. Behind the edge, you're in the new vacuum. Ahead of the edge, you're in the old vacuum. If you're at the edge when it passes, you don't have time to notice. You're transformed along with everything else in an instant. Inside the true vacuum bubble, the Higgs field has a different value. Particles have different masses, maybe zero mass, maybe infinite mass. The strong nuclear force might work differently. Atoms might not hold together. The entire structure of matter could be different. Chemistry as we know it wouldn't work. Stars couldn't form. Planets couldn't exist. Life would be impossible. If a vacuum metastability event started anywhere in the observable universe, the bubble would expand forever, eventually consuming everything. Stars, galaxies, all matter would be transformed into whatever exotic configuration is stable in the true vacuum. The universe would become a lifeless void, maybe a void where even atoms don't exist, just fields in their lowest energy states with no structure, no complexity, nothing. For Earth specifically, we'd never see it coming. The bubble expands at light speed. We wouldn't see the bubble approaching because the light carrying that information would arrive at the same instant as the bubble itself. One moment, normal universe. Next moment, the bubble passes through us at the speed of light, and we cease to exist in any meaningful way. Our atoms would be torn apart or reconfigured. Our planet would dissolve. The sun would vanish. Everything within the light cone of the event origin would eventually be consumed. The good news, if there is any, is that calculations suggest the Higgs field is probably stable, or at least has a lifetime far longer than the current age of the universe. We're likely safe from vacuum decay for trillions of years at minimum, probably. The calculations have uncertainties. New physics we haven't discovered could change the conclusion. And even if we're safe, somewhere in the universe, on timescales we can't comprehend, vacuum decay might be inevitable. The universe might eventually erase itself through quantum suicide, a phase transition that destroys everything and leaves only empty fields in true vacuum states, a cosmos where the conditions for complexity, structure, life, anything interesting, simply don't exist anymore. It would be the ultimate extinction, not just of humanity or Earth, or even our galaxy, but of the universe's ability to support anything at all. Nearby supernova remnant impact. Supernova explosions leave behind expanding shells of debris traveling at thousands of kilometers per second. If an ancient supernova remnant from an explosion thousands of years ago happens to intersect our solar system, Earth would be bombarded with high-energy particles and radiation. The shell would compress our heliosphere, the protective bubble of solar wind that shields us from galactic cosmic rays. Cosmic ray levels would spike, radiation would increase, cancer rates would climb. Extinction might not be immediate, but slow radiation poisoning over generations could destroy us. When a star explodes, it blasts its outer layers into space at extreme velocities. This expanding shell of gas, dust, and high-energy particles is the supernova remnant. It keeps expanding for thousands of years, gradually slowing as it sweeps up interstellar material. These remnants can be light years across, moving at thousands of kilometers per second. If Earth is in the path of one, we're in trouble. The first effect would be compression of the heliosphere. Our sun creates a protective bubble by blowing solar wind outward. This bubble deflects most galactic cosmic rays, shielding Earth. But a supernova remnant plowing into the heliosphere would compress it, maybe even collapse it temporarily. The solar wind would be pushed back by the remnant's pressure. Earth would be exposed to the full force of galactic cosmic radiation, plus the additional radiation from the remnant itself. Cosmic ray levels would increase dramatically. These aren't like solar radiation. Cosmic rays are high-energy particles, atomic nuclei accelerated to near light speed. When they hit the atmosphere, they create showers of secondary particles. Increased cosmic rays mean increased radiation at the surface. Plants would be damaged. Animals would develop cancers. Humans would face higher cancer rates, especially skin cancers and radiation-induced mutations. This wouldn't kill everyone immediately, but over decades or centuries of elevated radiation, the cumulative effects could be catastrophic. Crop yields would decrease as plants struggle with radiation damage. Cancer rates would climb until they become a leading cause of death across all ages. Mutations would increase, potentially leading to genetic degradation over generations. Birth defects would rise. The gene pool would accumulate harmful mutations faster than selection could remove them. Eventually, the population could face genetic collapse, unable to produce healthy offspring. We know of several supernova remnants in our region of the galaxy. The Vela supernova remnant is relatively close, about 800 light-years away. It exploded about 11,000 years ago. The remnant is still expanding. We're not currently in its path, but galactic motion is complex. Over thousands of years, our trajectory might intersect with old remnants we haven't mapped yet, and new supernovae happen. If a star exploded within 100 light-years, even if we survive the initial radiation, the remnant it creates would expand toward us. We'd have centuries or millennia before it arrived, depending on the distance. That seems like plenty of warning, but what could we do? We can't move the planet. We can't deflect a supernova remnant light-years across. We'd just have to prepare for the radiation increase, building better shielding, maybe moving underground, trying to survive the centuries of elevated cosmic ray bombardment. It's another slow extinction threat from cosmic events, a delayed consequence of stellar death that doesn't kill instantly, but grinds away at life over generations until nothing's left but a irradiated world where the background radiation is too high for complex life to persist. Rogue planet disruption. Not all planets orbit stars. Rogue planets were ejected from their birth systems and now drift through the galaxy alone. If a rogue planet passed through our solar system, its gravity could disrupt planetary orbits, sending Earth into a deadly trajectory. We could be thrown into the sun, thrown into deep space, or have our orbit made so elliptical that we'd swing between freezing and frying each year. Any of these scenarios means extinction. Rogue planets form when planetary systems are young and chaotic. Gravitational interactions between planets can result in one planet being ejected entirely, thrown out of its system at high velocity. That planet becomes a rogue, wandering the galaxy in darkness, no longer orbiting any star. Estimates suggest there might be billions of rogue planets in our galaxy, possibly more rogues than stars. They're dark, emit no light, and are almost impossible to detect unless they pass in front of a background star or their gravity lenses light from distant sources. One could be approaching our solar system right now, and we wouldn't know until it was close enough for its gravity to affect outer planets. If a rogue planet entered our solar system, chaos would follow. Its gravity would perturb the orbits of Jupiter and Saturn. Those giants would then perturb the inner planets. Earth's orbit could be altered unpredictably. A small change might make Earth's orbit more elliptical. Summers would become scorching as we swung closer to the sun. Winters would plunge to depths that freeze the oceans as we swung farther away. The wild temperature swings would make the planet uninhabitable. Nothing could adapt to conditions that vary so extremely. A larger change could throw Earth out of the habitable zone entirely. We might end up too close to the sun, turning Earth into a Venus-like hell. Or too far, turning us into a frozen ice ball like Mars. Both scenarios are extinction events. Humans can't survive on a planet being cooked or frozen beyond narrow habitable limits. The worst case would be Earth being ejected from the solar system entirely, becoming a rogue planet ourselves. We'd fly off into interstellar space, the sun shrinking behind us, temperatures would plummet, the oceans would freeze, the atmosphere would condense and fall as snow. Earth would become a lifeless ice world, drifting through the dark, our fate sealed by a random gravitational encounter with another world we never saw coming. We have no catalog of rogue planets. We don't know where they are. We can't predict if or when one might enter our solar system. We'd only detect it when it was already here, already disrupting orbits, already too late to do anything. Even if we had decades of warning, there's no defense. You can't deflect a planet. You can't change its trajectory. You just have to watch it approach and hope it doesn't get close enough to throw Earth into a deadly orbit. The galaxy is full of rogue planets, dark and silent, wandering between the stars. One of them might have our solar system in its path. We won't know until it's here. And when it arrives, if it gets too close, that's the end. Death by gravitational chaos, our planet's orbit shattered by a collision. Less encounter with a world that doesn't even know we're here, doesn't care, just passing through on its eternal journey through the void. Coronal mass ejection extinction. The sun occasionally ejects massive bursts of plasma and magnetic field into space, called coronal mass ejections or CMEs. A normal CME hitting Earth can disrupt satellites and power grids. But if the sun produced a super CME, far more powerful than anything in recorded history, it could strip away Earth's atmosphere. The magnetic field and charged particles would interact with our atmosphere, heating it to escape velocity. We'd watch our air blow away into space, leaving us on an airless rock. The sun's corona, its outer atmosphere, is superheated to millions of degrees by magnetic processes we still don't fully understand. Sometimes, magnetic field lines snap and reconfigure, flinging billions of tons of plasma into space at millions of kilometers per hour. These are coronal mass ejections. When they hit Earth, they interact with our magnetic field, creating geomagnetic storms. Most CMEs are manageable. They create auroras, maybe disrupt radio communications, occasionally damage satellites. But the sun is capable of much more. The Carrington event was a warning. A massive solar storm in 1859 caused auroras worldwide and melted telegraph wires. If that storm hit today, it would cause billions in damage to our electrical infrastructure. But the sun could do worse, much worse. If a super CME hit Earth, magnitude stronger than anything we've recorded, the consequences would be apocalyptic. The charged particles would slam into our magnetic field with such violence that the interaction would heat our upper atmosphere to thousands of degrees. Atmospheric molecules would gain enough energy to reach escape velocity. The atmosphere would start bleeding into space. The process might take days or weeks, but it would be unstoppable. We'd watch the sky thin out. The air would become unbreathable. Pressure would drop. The ozone layer would be completely destroyed. UV radiation from the sun would flood the surface, killing anything exposed. As the atmosphere thinned, temperatures would swing wildly between day and night. Water would boil in sunlight and freeze in shadow. The oceans would start to evaporate, adding water vapor to the atmosphere temporarily before that too was stripped away. Eventually, Earth would be airless. The oceans would freeze or evaporate completely, depending on the temperature. The surface would be a barren wasteland, scoured by solar wind and cosmic rays, nothing alive, nothing able to live. We'd become Mars, a planet that once had an atmosphere and possibly life, now a dead rock with only traces of its past. The terrifying part is, we can't predict when the sun might produce a super CME. Solar activity is cyclical, with roughly 11-year cycles, but individual events are chaotic. The sun could erupt tomorrow with a CME that dwarfs anything we've seen. We'd have maybe a day's warning as the plasma cloud travels from the sun to Earth. Not enough time to evacuate. Not enough time to build shelters that could survive atmospheric stripping. Just enough time to realize we're about to die. Some scientists argue that a CME powerful enough to strip Earth's atmosphere is unlikely. The sun is a relatively stable star. It doesn't produce the kind of superflares that younger or more active stars do. We're probably safe from atmospheric stripping by solar activity. Probably. But probably isn't certain. The sun has surprised us before. It could surprise us again with an eruption so powerful, It ends life on Earth not through heat or radiation directly, but by blowing away the air we breathe, leaving us gasping on a world that no longer has an atmosphere to support us. Pulsar radiation sweep. Pulsars are rotating neutron stars that emit beams of radiation from their magnetic poles. As the pulsar rotates, the beams sweep through space like a lighthouse. If Earth happened to be in the path of a pulsar beam, we'd be hit with intense radiation periodically as the pulsar spins. Depending on the pulsar's power and distance, this could range from disruptive to lethal. A nearby, powerful pulsar could irradiate Earth every time its beam swept across us, making the planet uninhabitable. Pulsars are the corpses of massive stars, neutron stars spinning at incredible rates, sometimes hundreds of times per second. Their magnetic fields are trillions of times stronger than Earth's, and these fields funnel radiation into narrow beams that shoot from the magnetic poles. If those poles are misaligned with the rotation axis, the beams sweep around like a searchlight. From Earth, we detect this as a regular pulse, hence the name pulsar. Most pulsars are far enough away that their beams, even if they sweep past us, are too weak to cause harm. We just detect the radio pulses and study them as interesting astronomical objects. But a pulsar close enough and powerful enough could be deadly. If its beam swept across Earth, we'd receive a dose of radiation every rotation. Depending on the pulsar's rotation period, this could be every second, every millisecond, a steady bombardment of high-energy photons and particles. The radiation would damage the ozone layer. Each pulse would strip away a little more protection. Over time, the cumulative effect would destroy the ozone completely, exposing the surface to lethal UV radiation from the sun. But the pulsar's own radiation would be the more immediate threat. X-rays and gamma rays from the beam would penetrate the atmosphere, irradiating the surface directly. Living things would accumulate radiation damage with each pulse. Plants would die. Animals would develop cancers and die. Humans would face radiation sickness, cancers, genetic damage, death. The pulsing nature makes it insidious. It's not one massive dose that kills instantly. It's repeated doses, over and over, day after day, each pulse adding more damage. You can't hide from it. The radiation penetrates deep. Shelters might provide some protection, but unless you stay underground permanently, you're exposed. And underground shelters can only support small populations for so long. Eventually, supplies run out, equipment fails, people die. Fortunately, we haven't detected any pulsars close enough to threaten us. The nearest known pulsar is several hundred light-years away, far enough that its beam, if it swept past Earth, would be negligible. But pulsars are hard to detect if their beams aren't pointing at us. There could be nearby pulsars we haven't found yet because their beams sweep in directions we don't observe. We might only discover a nearby pulsar when it's already irradiating us, its beam having precessed or our motion through the galaxy having brought us into its path. And pulsars are born from supernova explosions. If a nearby star went supernova and formed a pulsar, and if that pulsar's beam happened to sweep across Earth, we'd face extinction from the corpse of a star that might not have even existed as a neutron star when humans first evolved. Killed by a stellar lighthouse we had no idea was shining in our direction until the light reached us and started killing us, pulse by pulse, rotation by rotation, until nothing was left alive on a planet bathed in the regular, deadly rhythm of a spinning neutron star's radiation beam. Galactic center explosion. The center of our galaxy contains not just a supermassive black hole, but also dense clusters of stars, gas, and dust. Periodically, the galactic center experiences outbursts, explosions, or ejections of material and energy. If a major galactic center explosion occurred, it could send a shock wave of radiation and particles rippling through the galaxy. Earth, 26,000 light-years away, would eventually be hit by this wave. Depending on the explosion's magnitude, it could be an extinction event. Astronomers have observed evidence of past galactic center outbursts. The Fermi bubbles are giant lobes of gas and radiation extending above and below the galactic plane, likely created by an eruption from the galactic center millions of years ago. These bubbles are enormous, 50,000 light-years across. Whatever created them was an explosion or outburst of tremendous energy. If a similar outburst happened today, the radiation would spread outward at the speed of light. Earth would be hit in about 26,000 years, the time it takes light to travel from the galactic center to us. But we wouldn't know it was coming until the radiation arrived. No warning. Just sudden bombardment of high-energy photons and particles from the direction of the galactic core. The radiation could last for thousands of years as the outburst continues, or as the expanding shell of material passes through our region of the galaxy. During this time, cosmic ray levels would spike. The background radiation would increase. The effects would accumulate. Ozone depletion, increased surface radiation, ecological disruption, higher cancer rates, mutations. Over centuries or millennia, the sustained radiation could cause mass extinction, not through a single catastrophic event, but through prolonged exposure that gradually makes the planet uninhabitable. Alternatively, if the outburst included a directed jet or beam, and if Earth happened to be in its path, the effects could be immediate and catastrophic. Jets from galactic centers can carry enormous energy, focused into narrow cones. A jet hitting Earth would be like being in the path of a gamma-ray burst, except the source is our own galactic core. Sterilization would be quick and total. We don't fully understand what causes galactic center outbursts. They might be related to the central black hole swallowing large amounts of matter. They might be related to star formation and supernovae in the dense central regions. Whatever the cause, they happen. The evidence is in the Fermi bubbles and other structures we see. The question isn't if another outburst will happen, but when. And given the 26,000-year light travel time, if the galactic center erupted today, we wouldn't know until our distant descendants, if any exist, are hit by the radiation wave. We could already be doomed. The extinction event already launched, traveling toward us at light speed, set to arrive thousands of years from now. There's no way to know. We can only watch the galactic center, study its behavior, and hope that if another major outburst occurs, it's mild enough that we survive, or that it happens after humanity has become an interstellar species capable of evacuating threatened worlds. Because if it happens while we're still confined to Earth, and if it's powerful enough, we're extinct, killed by our own galaxy's heart in a fit of violence we can't predict, can't prevent, can't survive. Close stellar encounter. Stars move through the galaxy. Occasionally, they pass close to each other. If a star passed close to our solar system, its gravity could disrupt the Oort cloud, the distant shell of comets surrounding the Sun. This would send trillions of comets falling toward the inner solar system. Earth would face bombardment lasting thousands of years. Even if no comet directly hit us, the repeated close passes and the dust they release would block sunlight, plunge us into an ice age, and potentially cause extinction through environmental collapse. The Oort cloud extends up to a light year from the Sun, a vast reservoir of icy bodies left over from the solar system's formation. These comets are stable in their distant orbits, too far from the Sun to be affected by its gravity much. But they're weakly bound. A passing star could gravitationally perturb them, sending them falling inward toward the Sun. Most would miss Earth, but with trillions of comets, even a tiny percentage hitting the inner solar system means thousands or millions of large icy bodies passing through our region over thousands of years. Some would impact planets. Some would come close enough to Earth to be dangerous. Even without direct impacts, the comet bombardment would have severe effects. Comets release gas and dust as they approach the Sun. This material would fill the inner solar system, partially blocking sunlight. The effect would accumulate over centuries as more and more comets fell inward. The dust would create a haze that reduced solar input to Earth. Temperatures would drop. An ice age would begin, triggered not by orbital changes but by artificial dust clouds from cometary debris. Plants would struggle with reduced sunlight. The food chain would face stress. Humans might survive initially, but a prolonged ice age combined with the threat of comet impacts would strain civilization. Agriculture would fail in many regions. Billions could starve as the planet cooled and dust blocked the sun for thousands of years until the comet storm finally ended. The likelihood of a close stellar encounter in the near future is very low. Space is vast. Stars are far apart. The closest star to us is over 4 light-years away. Even encounters within a few light-years are rare on human timescales. But over millions of years, close encounters are inevitable. The sun orbits the galaxy, passing through different stellar neighborhoods. Eventually, it will pass close to another star, close enough to perturb the Oort cloud. This might have happened in the distant past. Some scientists speculate that past comet bombardments might be linked to extinction events in Earth's geological record. Mass extinctions that correlate with evidence of increased comet activity. If true, we're due for another stellar encounter eventually. It might be 1,000,000 years from now. It might be sooner. We wouldn't have much warning. By the time we detected a star approaching close enough to threaten the Oort cloud, the perturbation might already be underway. Comets would be falling toward us, and all we could do is prepare for millennia of bombardment and cooling, hoping we survive until the comet storm passes and the sun clears the dust, leaving us on a frozen, battered world that might or might not still be capable of supporting human civilization. Antimatter-asteroid collision. Antimatter annihilates with normal matter, releasing energy according to Einstein's equation E equals mc squared. If an asteroid made of antimatter existed and it hit Earth, the annihilation would release energy equivalent to millions of nuclear bombs. The entire asteroid and an equal mass of Earth would be converted to pure energy instantly. The explosion would be visible from across the solar system. Nothing in the impact region survives. Depending on the antimatter asteroid's size, it could be an extinction-level event. Antimatter is rare in the universe. The Big Bang should have produced equal amounts of matter and antimatter, but for reasons we don't understand, the universe is dominated by matter. Antimatter exists only in tiny quantities, created briefly in high-energy collisions. But if a region of space somehow contained antimatter, if there were antimatter asteroids or comets, they'd be invisible until they hit something. Antimatter and matter look identical from a distance. You can't tell if an asteroid is made of antimatter until it interacts with matter. If an antimatter asteroid entered the solar system, it would probably start annihilating as soon as it hit the thin interplanetary gas. This would create a trail of gamma rays marking its path. We might detect this and realize an antimatter object is approaching, but there wouldn't be much time. Asteroids move fast. From detection to impact could be days or hours. Not enough time to do anything except realize we're about to be hit by something that will explode with energy beyond anything nuclear weapons can produce. The impact would be catastrophic. An antimatter asteroid the size of a car, maybe a ton of antimatter, hitting Earth would annihilate with a ton of Earth's matter. That's 2 tons totally converted to energy, about 90 trillion joules, equivalent to a large nuclear weapon. An antimatter asteroid the size of a mountain would release energy that dwarfs our entire nuclear arsenal. The explosion would vaporize everything within thousands of kilometers. The shockwave would circle the globe. The debris thrown into the atmosphere would block sunlight for years. Mass extinction would follow from the impact winter. Fortunately, antimatter asteroids probably don't exist. We've never seen any evidence of them. If they existed in significant numbers, we'd see gamma-ray signatures from them annihilating with interstellar gas. The universe seems to be pure matter, at least in our region. Antimatter is confined to tiny amounts in particle accelerators and cosmic ray collisions. We're probably safe from antimatter impacts, probably, but we don't know everything about the universe. There might be regions of antimatter we haven't detected. There might be antimatter objects in the vast spaces between galaxies where they wouldn't interact with anything and thus wouldn't produce detectable signatures. If one of those objects happened to enter our solar system, we'd find out the hard way that antimatter annihilation is not just a physics curiosity, but an extinction threat capable of releasing energies that make all other impacts look gentle by comparison. Solar luminosity increase. The sun is gradually getting brighter. Over billions of years, as it ages, it converts hydrogen to helium in its core. This changes the core's composition, making fusion more efficient, increasing the sun's luminosity. In about 1 billion years, the sun will be 10% brighter than now. That doesn't sound like much, but it's enough to trigger a runaway greenhouse effect on Earth. The oceans will evaporate. The planet will become a Venus like hell. All life will die. This isn't sudden extinction. It's slow, inevitable death written into stellar physics. As the sun ages, its core contracts slightly, increasing temperature and pressure, making fusion burn hotter. This releases more energy, brightening the sun. The effect accumulates slowly, a fraction of a percent per 100 million years. But over 1 billion years, the cumulative brightening is significant. Earth's climate is sensitive to solar input. A few percent change in sunlight can mean the difference between ice ages and warm periods. A 10% increase is catastrophic. The extra energy heats the planet. More water evaporates. Water vapor is a greenhouse gas, trapping more heat, causing more evaporation, a positive feedback loop. The runaway greenhouse effect has no natural break. The oceans evaporate. The atmosphere becomes thick with steam. Surface temperatures soar to hundreds of degrees. The planet becomes uninhabitable, possibly permanently. Earth transforms from a water world into a steam hell. Then, as the water is lost to space via UV dissociation, into a dry, dead rock like Venus. This fate is inevitable if we stay on Earth. The sun will keep brightening. In 1 billion years, maybe sooner, Earth becomes uninhabitable. This is written into our star's life cycle. We can't change it. We can't dim the sun. We can only accept that Earth has an expiration date and plan accordingly. The timescale is so long it seems irrelevant. 1 billion years is longer than complex life has existed on Earth. Surely we'll have solved this by then. We'll have colonized other worlds. We'll have left the solar system. We'll have transcended biological form. The distant future extinction doesn't threaten anyone alive today or for countless generations, but it's still extinction. Eventually, if humanity remains confined to Earth, the brightening sun will kill us as certainly as any asteroid or supernova. The advantage of this threat is it gives us time. We see it coming 1 billion years in advance. We can prepare. We can leave. We can ensure that when Earth dies, humans or our descendants continue elsewhere. But it also reminds us that even our sun, the source of all life on Earth, is not eternal. It's aging. It will kill us eventually. And long after that, in another 5 billion years, it will expand into a red giant and swallow Earth entirely, vaporizing the planet in the sun's outer layers. Earth's fate is sealed. The question is whether we escape before the sun's inevitable changes destroy the world that gave us birth. Jupiter migration catastrophe. Planetary systems can be unstable. If Jupiter's orbit changed significantly, migrating inward or outward due to gravitational interactions, it would destabilize the entire solar system. Earth's orbit could be perturbed into uninhabitable regions. We might be thrown too close to the sun or too far away. Or Jupiter's migration might send asteroids and comets raining into the inner solar system in unprecedented numbers. Either way, Earth becomes uninhabitable. Planetary migration isn't just theoretical. We've observed it in other star systems. Hot Jupiters, gas giants orbiting very close to their stars, probably formed farther out and migrated inward. The process is chaotic and destructive. Planets migrating through a system scatter or eject other planets, disrupt orbits, create havoc. If Jupiter started migrating, the solar system would become unstable. The mechanisms that could cause Jupiter to migrate aren't clear. Gravitational interactions with the Kuiper belt or Oort cloud might do it over long timescales. A close encounter with a passing star might perturb Jupiter's orbit. An undiscovered planet in the outer solar system might gravitationally interact with Jupiter, setting up resonances that cause migration. Whatever the cause, if Jupiter moves significantly from its current orbit, the consequences would be catastrophic for Earth. Jupiter's gravity currently protects us by deflecting or capturing comets and asteroids that might otherwise hit Earth. Its stable orbit maintains the overall stability of the inner solar system. If Jupiter moved inward, closer to the Sun, its gravity would pull on Earth, Mars, and the asteroid belt. Orbits would change. The asteroid belt might be destabilized, sending rocks scattering through the inner solar system. Earth could be bombarded by asteroids as Jupiter's migration creates chaos. If Jupiter moved outward, the protective influence would be removed. Comets from the outer solar system would have free reign. Earth would face increased impact threats. And without Jupiter's stabilizing presence, Earth's own orbit might become chaotic over long timescales, swinging between extremes that make the planet uninhabitable. The likelihood of Jupiter migrating in the near future is very low. The solar system has been stable for billions of years. Jupiter's orbit is well settled, but stable doesn't mean permanent. On billion-year timescales, even stable systems can evolve. Perturbations accumulate, resonances develop. The chaotic nature of orbital mechanics means that, given enough time, unexpected changes can occur. We can't predict if or when Jupiter might migrate, but we can say that if it does, Earth's fate is sealed. We're dependent on Jupiter staying where it is, maintaining the stability it's provided for billions of years. If that stability breaks, we're facing extinction from our own solar system's dynamics, killed not by external threats, but by the gravitational chaos of planets shifting in a dance that no longer favors our continued survival. Heliosphere collapse. The Sun's solar wind creates a protective bubble called the heliosphere, which shields the solar system from most galactic cosmic rays. If the Sun's activity decreased significantly, entering a prolonged minimum far deeper than normal solar minimums, the heliosphere could shrink or collapse. Earth would be exposed to much higher levels of galactic cosmic radiation. The increased radiation would damage the ozone layer, increase surface radiation, and potentially make the planet uninhabitable over time. The Sun goes through cycles of activity, roughly 11 years from minimum to maximum and back. During solar minimum, the Sun is quieter, fewer sunspots, less solar wind. But even at minimum, the Sun maintains enough activity to keep the heliosphere inflated. However, the Sun has experienced prolonged deep minimums in the past. The Maunder minimum in the 17th century saw almost no sunspots for decades. If the Sun entered a minimum far deeper and longer than any in recorded history, the heliosphere could shrink dramatically. The consequences would unfold over years or decades. As the heliosphere collapsed, galactic cosmic rays would penetrate deeper into the solar system. Earth's atmosphere would be hit with increasing radiation. Cosmic rays would create showers of secondary particles, increasing background radiation at the surface. The ozone layer would be damaged by the radiation, creating feedback as more UV reached the surface, further stressing ecosystems. The increased radiation would affect all life. Mutation rates would climb. Cancer rates would soar. Plants would struggle with DNA damage. The food chain would face stress from the bottom up as primary producers are damaged by radiation. Over decades, the cumulative effects could trigger ecological collapse. Humans might adapt with better shielding, underground habitats, technological solutions. But if the heliosphere collapse were severe and prolonged, lasting centuries, the challenge would be sustaining civilization and population on a planet with permanently elevated radiation. We don't know what could cause a prolonged, deep solar minimum. The Sun's magnetic dynamo is complex and not fully understood. It might have modes of operation we haven't observed yet. If the Sun switched into a low activity mode and stayed there for centuries or millennia, we'd face slow extinction from radiation exposure. A gradual decline as the protective bubble that shielded us for billions of years deflates, leaving us exposed to the galaxy's harsh radiation environment. It's another reminder that our safety depends on the Sun's continued normal operation. If the Sun changes its behavior in ways we don't expect, we're vulnerable. We've built our civilization on a planet within a protective bubble. If that bubble collapses, we're suddenly living in a much more dangerous cosmic environment, and we might not survive the transition. Orbital resonance catastrophe. Orbital resonances occur when planets' orbital periods form simple ratios. These resonances can amplify small gravitational perturbations, leading to dramatic orbital changes over time. If Earth entered a harmful resonance with another planet, our orbit could become unstable. We might be thrown into an eccentric orbit that makes the planet uninhabitable, or we might be ejected from the solar system entirely. The changes would accumulate over thousands or millions of years, but the end result is extinction. Orbital resonance is common in the solar system, usually in stabilizing ways. Jupiter's moons are in resonances that keep their orbit stable, but resonances can also destabilize. The asteroid belt has gaps, Kirkwood gaps, at orbital distances that resonate with Jupiter. Asteroids that entered those resonances were ejected. Earth has avoided harmful resonances so far. Our orbit is stable, not in strong resonance with any other planet. But orbits change slowly. Gravitational interactions between planets cause orbital precession, shifting the orbit slightly over time. Given millions of years, Earth could drift into a resonance with Venus, Mars, or even Jupiter. If this resonance is destabilizing, Earth's orbit could begin to change. The eccentricity might increase, making our orbit more elliptical. We'd swing closer to the Sun at perihelion and farther at aphelion. The temperature swings would become extreme. Summers would be scorching as we approach the Sun. Winters would freeze the planet as we swung farther away. The wild variations would make the planet uninhabitable. Alternatively, a resonance might increase Earth's orbital inclination, tilting our orbit relative to the plane of the solar system. This would change seasonal patterns and could lead to orbital instability as interactions with other planets become more complex. The worst outcome would be ejection. If the resonance transferred enough energy to Earth's orbit, we could be thrown out of the solar system entirely, becoming a rogue planet. The Sun would disappear. We'd fly off into interstellar space, freezing in the darkness, another dead world among the countless rogues drifting through the galaxy. The timescales for resonance-driven instability are long, millions of years. We're not facing immediate threat, but the chaotic nature of orbital mechanics means we can't predict with certainty that Earth's orbit will remain stable forever. Small changes accumulate. Resonances develop. The solar system is not a clockwork that runs forever unchanged. It's a dynamical system that evolves, and evolution can be deadly. We're betting our survival on the solar system's continued stability, on the assumption that the orbital configuration that's kept Earth in the habitable zone for billions of years will continue. But that's not guaranteed. Given enough time, resonances, perturbations, and chaos could reshape the solar system, and when they do, Earth might not survive the reshaping. Neutron star flyby. Neutron stars are dense stellar corpses, packing more mass than the Sun into a sphere 20 kilometers across. If a neutron star passed through our solar system, even without direct collision, its intense gravity would disrupt everything. Planetary orbits would be thrown into chaos. Tidal forces would tear apart moons and possibly planets. Earth could be pulled apart by tides if the neutron star passed close enough, or we could be thrown into a deadly orbit. Either way, extinction is certain. A neutron star flyby would be visible long before it arrived. Neutron stars, especially pulsars, emit radiation we can detect. We'd probably see it coming decades or centuries in advance. But seeing it coming doesn't help. There's no way to deflect a neutron star. It's a stellar mass object. You can't push it off course. You can only watch it approach and calculate which planets will survive and which won't. As the neutron star entered the outer solar system, its gravity would perturb the orbits of Jupiter, Saturn, and the outer planets. These giants would be pulled from their stable orbits, their protective influence over the inner system gone. Asteroids and comets would be scattered, some ejected, some thrown toward the Sun, creating bombardment of the inner planets. When the neutron star reached the inner solar system, Earth would face its gravitational wrath. If the neutron star passed close enough, tidal forces would become extreme. The side of Earth facing the neutron star would be pulled harder than the opposite side. The planet would be stretched. If the tidal forces exceeded Earth's structural strength, The planet would be torn apart, ripped into fragments by gravity. More likely, the neutron star would pass at a distance that doesn't tear Earth apart, but does throw our orbit into chaos. We might be flung toward the sun, flung into deep space, or left in a highly elliptical orbit that's uninhabitable. Any of these outcomes is extinction. The neutron star would pass through the solar system in days or weeks depending on its velocity. Its visit would be brief, but the destruction would be permanent. The solar system would be left in ruins, planets scattered or destroyed, any surviving worlds thrown into orbits that don't support life. The probability of a neutron star passing through our solar system is extremely low. Neutron stars are rare, and space is vast. The odds of one coming close enough to disrupt us are minuscule on human timescales. But the universe is old. Given billions of years, even extremely unlikely events can happen. We've been lucky so far. No neutron star has wandered through our neighborhood. But our luck might not hold forever. Somewhere out there, neutron stars drift through the galaxy, invisible unless they're pulsing radiation in our direction. One might be heading toward us right now, its trajectory set to intersect our solar system thousands of years from now. We wouldn't know until we detected it approaching, and by then, it would be too late to do anything except calculate our remaining time and watch a stellar corpse deliver our extinction through gravitational violence we can observe but not prevent. Dark energy acceleration catastrophe. Dark energy is the mysterious force causing the universe's expansion to accelerate. If dark energy's properties changed, if it strengthened significantly, the acceleration could become catastrophic. The Big Rip scenario predicts that if dark energy keeps strengthening, it will eventually overcome all forces holding structures together. First, galaxies would be torn apart, then solar systems, then planets, then atoms themselves. Everything would be ripped to pieces by accelerating expansion. The universe would end not in fire or ice, but in disintegration. Dark energy makes up about 70% of the universe's energy density. We don't know what it is. We named it dark energy because we can't see it and don't understand it. We only know it exists because we observe galaxies accelerating away from us, and that requires some kind of repulsive force pushing space apart. If dark energy is constant, a cosmological constant as Einstein proposed, then the universe will keep accelerating gently. Galaxies will drift apart over trillions of years. Space will become increasingly empty and cold, but we'll have trillions of years before that matters. If dark energy is not constant, if it can change strength, then we're in unknown territory. If it strengthens, the acceleration will increase. Eventually, expansion could become so violent that it overcomes gravity, then electromagnetic forces, then nuclear forces. First, galaxy clusters would be torn apart as expansion overpowers the gravity holding them together. Then, individual galaxies would dissolve. Stars would be ripped from their orbits. Within our solar system, planets would be pulled away from the sun. Earth's orbit would expand, carrying us into cold and darkness. But before we froze, the acceleration would keep increasing. The sun itself would be pulled apart. Earth would be torn apart. Molecules would be ripped apart. Atoms would be shredded. Everything would disintegrate in an accelerating expansion that overpowers every force in physics. The Big Rip would be the ultimate extinction, not just of humanity or life or Earth, but of all structure in the universe. Everything reduced to disconnected subatomic particles flying apart faster than light in the expanding space between them. This scenario depends on dark energy's equation of state, how its density changes as the universe expands. Current observations suggest dark energy is probably constant or close to it, but the uncertainty is large. We can't rule out that dark energy might strengthen. If it does, and if the strengthening continues, the Big Rip becomes inevitable. The timescale for this is estimated at tens of billions of years if it happens at all. That's so far in the future that it seems irrelevant. The sun will die long before then. Earth will be gone. Humanity will have either died out or transcended into something unrecognizable. But it's still worth noting that the universe itself might have an expiration date, a point at which even the laws of physics can't prevent everything from being torn apart by the accelerating expansion of space. And if dark energy is more exotic than we think, if it can change more rapidly than models predict, the timeline could be shorter. We might have millions rather than billions of years. We don't know. Dark energy is a mystery, and mysteries, as always, can kill you. Collapsing magnetosphere. Earth's magnetic field protects us from solar wind and cosmic rays. It's generated by the molten iron core's convection and rotation. But magnetic fields can collapse. Mars lost its magnetic field billions of years ago, leaving its atmosphere vulnerable to solar wind stripping. If Earth's magnetic field collapsed, either through core cooling or a pole reversal that went wrong, we'd lose our primary radiation shield. The atmosphere would be stripped away over millions of years. Cosmic rays would bombard the surface. Earth would become uninhabitable. The Earth's magnetic field has reversed polarity many times in the past, flipping north and south magnetic poles. During these reversals, the field weakens significantly, sometimes to just 10% of normal strength. The field might even become multipolar during the transition, with several magnetic poles instead of two. These reversals happen every few 100,000 years on average. We're overdue for one. The last reversal was 780,000 years ago. Current measurements show the field is weakening, which might indicate a reversal is beginning. During a reversal, Earth would be vulnerable. The weakened field would allow more cosmic rays and solar particles to reach the atmosphere. The ozone layer would be damaged. Surface radiation would increase. This wouldn't be immediately catastrophic. Reversals take thousands of years. The field doesn't disappear, just weakens and reorganizes. Life has survived many reversals in the past. But if a reversal coincided with a solar storm or a period of high cosmic ray flux, the combined effects could be severe. And there's a scarier possibility. What if the field didn't recover after a reversal? What if the core's dynamo failed to restart the field? Mars provides a warning. Its core cooled and solidified, stopping the dynamo that generated its magnetic field. Without the field, solar wind stripped away the atmosphere over hundreds of millions of years. Mars became the cold, dead desert it is today. Earth's core is larger and should stay molten for billions of years. But what if we're wrong? What if there's a process we don't understand that could stop the dynamo? If Earth's magnetic field collapsed permanently, the planet would be doomed. The atmosphere would be slowly stripped away by solar wind. Cosmic rays would irradiate the surface. Life would retreat underground, trying to escape the radiation, but without an atmosphere, the planet becomes inhospitable. Temperatures would swing wildly. Water would freeze or evaporate. Over millions of years, Earth would transform into a dead rock like Mars. Our magnetic shield gone, the atmosphere gone, life extinct. This is a slow extinction, playing out over geological time. But it's still extinction, and it's a reminder that Earth's habitability depends on the core remaining hot and active, generating the magnetic field that's protected us for billions of years. If that protection fails, we're as doomed as Mars, just on a slower timescale. Kuiper Belt disruption. The Kuiper Belt is a region beyond Neptune filled with icy bodies, remnants from the solar system's formation. If something disrupted the Kuiper Belt, a passing star, a rogue planet, or gravitational perturbation from an unknown outer planet, the result would be a swarm of comets falling toward the inner solar system. Earth would face bombardment lasting thousands of years. Even without direct impacts, the increased comet activity would fill the inner system with dust, blocking sunlight and triggering climate changes that could cause extinction. The Kuiper Belt is relatively stable now, but stability can be broken. If a massive object passed through or near the Kuiper Belt, its gravity would scatter the icy bodies. Some would be ejected from the solar system entirely. Others would have their orbits changed, sending them falling inward toward the sun. The result would be thousands or millions of new comets entering the inner solar system over the following millennia. Earth's encounter rate with large comets would skyrocket. Instead of one significant comet every few million years, we might face several per century. The impact threat would be constant. Civilization would have to deal with regular comet strikes, each one potentially devastating. Even if we developed technology to deflect most of them, some would get through. The cumulative damage over thousands of years would be catastrophic. But the direct impacts might not be the worst of it. Comets release gas and dust as they approach the sun. With thousands of comets in the inner solar system simultaneously, the amount of dust would be enormous. This dust would spread throughout the inner solar system, creating a haze that blocked a significant fraction of sunlight. Earth's climate would cool. An ice age would begin, not from orbital changes, but from artificial dust clouds created by the comet bombardment. The ice age would persist as long as comets kept falling inward, potentially thousands of years. Agriculture would fail in many regions. Ecosystems would collapse under the stress of cooling and reduced sunlight. Humanity might survive in reduced numbers, clinging to habitable regions near the equator, but billions would die from starvation and cold. The Kuiper Belt disruption would be a slow-motion extinction event, playing out over millennia as wave after wave of comets fell through the inner solar system, bombarding the planets and filling space with dust that choked the light from the sun, plunging Earth into a long darkness punctuated by impacts that carved craters and killed millions, a cosmic siege that we could observe happening but couldn't stop, watching helplessly as the outer solar system's chaos reached inward to destroy the habitability of the one planets with dust that choked the light from the sun. Binary star capture. Our sun is a solitary star, but most stars in the galaxy are in binary or multiple systems. If another star passed close enough to our sun, the two might gravitationally capture each other, forming a binary system. This would fundamentally reshape the solar system. Planetary orbits would be destabilized by the second star's gravity. Earth could be thrown into an orbit around both stars, experiencing wild temperature swings as we orbited the pair. Or we could be ejected entirely, flung into interstellar space. Either way, extinction follows from the catastrophic restructuring of our system. Stellar captures are rare but not impossible. If a star passed through the solar system at just the right velocity and angle, it could be slowed by gravitational interaction with the sun and outer planets, enough to become gravitationally bound. The two stars would begin orbiting each other, settling into a binary configuration over thousands of years. During this process, the solar system would be thrown into chaos. Planets would be pulled by the gravity of both stars. Orbits would change unpredictably. Jupiter and Saturn might be the first casualties, thrown into new orbits or ejected entirely. Without their stabilizing influence, the inner solar system would become unstable. Earth's orbit would shift. Best case scenario, we end up in a circumbinary orbit, orbiting both stars together. This might be stable long-term, but the climate effects would be catastrophic. With two stars providing varying amounts of heat depending on their orbital configuration, Earth would experience extreme temperature variations. When both stars were close, we'd bake. When they were far, we'd freeze. The wild swings would make the planet uninhabitable. Worst case scenario, Earth is ejected during the chaos, thrown out of the system entirely. We become a rogue planet, freezing in the darkness as we drift through interstellar space, our fate sealed by the random encounter with a passing star that decided to move in and share our solar system without regard for the planets that were already here. The probability of stellar capture is vanishingly small on human timescales. Stars are far apart, and the specific conditions needed for capture are rare. But the galaxy is old, and the sun will orbit the galactic center many more times before it dies. Over billions of years, the probability of a close stellar encounter increases. Eventually, we might face this threat. The sun might gain a companion star, and when it does, the solar system as we know it will be destroyed, reshaped by the gravitational forces of two stars locked in orbital dance, with no regard for the fragile habitable planet that once circled one of them in a stable, life-supporting orbit. Moon destabilization. Earth's moon stabilizes our axial tilt, preventing wild swings in seasonal extremes. If the moon were destabilized, either by a massive impact, gravitational interaction with another body, or slow orbital decay, Earth would face catastrophic climate changes. Without the moon's stabilizing influence, our axial tilt could vary chaotically. Seasons would become extreme and unpredictable. Ice ages would alternate with scorching periods. The climate changes would happen too fast for life to adapt. Extinction would follow from environmental chaos caused by losing our moon's gravitational anchor. The moon's orbit is slowly expanding. It moves away from Earth at about 4 centimeters per year as tidal forces transfer angular momentum. This is a natural process and won't become dangerous for billions of years. But if something accelerated this process, a massive asteroid impact on the moon, a gravitational perturbation from a passing body, the moon could be destabilized much faster. If the moon's orbit became highly elliptical, the tides would vary dramatically. When the moon was close, tides would be enormous, flooding coastal areas. When the moon was far, tides would be minimal. The varying tidal forces would stress Earth's crust, possibly triggering increased volcanic and seismic activity. The changing distance would also affect the stabilization of Earth's axial tilt, though less severely than if the moon were lost entirely. If the moon were ejected from orbit, the consequences would be dire. Earth's axial tilt is currently about 23 degrees, giving us moderate seasons. Without the moon, gravitational interactions with other planets would cause the tilt to vary chaotically over tens of thousands of years. The tilt could swing from nearly 0 degrees, meaning almost no seasons, and the poles in permanent darkness, to extreme tilts of over 60 degrees, meaning wild seasonal extremes where the poles would point almost directly at the sun during summer and away during winter. The climate swings would be too rapid and extreme for ecosystems to adapt. Ice ages would come and go on timescales of thousands of years instead of tens of thousands. Agriculture would be impossible. Civilization would collapse as the climate became unpredictable and hostile. The moon is more than a pretty object in the night sky. It's a critical component of Earth's environmental stability. We've taken it for granted for all of human history, never considering that its presence is essential for our survival. If we lost it, we'd discover just how much we depend on our largest satellite to keep our planet's climate within the narrow range that allows complex life to thrive. Higgs field fluctuation. The Higgs field gives particles their mass through interactions with the field. If the Higgs field's value changed significantly due to quantum fluctuations or external perturbations, the masses of fundamental particles would change. Electrons might become heavier or lighter. Quarks might change mass. This would alter how atoms and molecules form. Chemistry would break. Matter as we know it would cease to exist. Earth would disintegrate as the fundamental forces holding atoms together change. We'd be destroyed by a shift in the very field that defines how particles interact with reality. The Higgs field is thought to be stable at its current value, but some theories suggest it might be metastable, sitting in a local energy minimum rather than the absolute lowest state. If true, a sufficiently large energy fluctuation could kick the field into a different configuration. This wouldn't be vacuum decay, which changes space-time itself, but a change in the Higgs field's value throughout some region of space. The effects would depend on how much the field value changed. A small change might alter particle masses by a few %. This would be catastrophic enough. Atoms would have different properties. Chemical bonds would be weaker or stronger. Molecules like DNA and proteins might not be stable. Life as we know it couldn't function. A large change would be immediately fatal. If electrons became much heavier, atoms would shrink dramatically or wouldn't form at all. If quarks changed mass significantly, protons and neutrons would have different properties, possibly not forming stable nuclei. Matter would simply cease to exist in any form we recognize. Earth would dissolve into exotic particles or energy as atomic structure collapsed. The Higgs field is quantum in nature, subject to fluctuations. On small scales and short times, it fluctuates constantly. But these fluctuations average out. Macroscopic changes to the field value require enormous energy inputs or statistically unlikely quantum events. The probability of a dangerous Higgs field fluctuation in our region of space is extremely low. We're probably safe, probably. But quantum mechanics allows for unlikely events. Given enough time and space, fluctuations that seem impossible become inevitable somewhere. If one happens here, we won't see it coming. The field would just change, and everything would end as the fundamental property that gives particles mass shifts to a new value, incompatible with the existence of matter, ending not just us, but everything made of atoms within the affected region. A sudden cessation of existence caused by the universe's most fundamental fields deciding, through quantum chance, to adopt new configurations where we cannot exist. Solar system collision with nebula. Dense molecular clouds and nebulae drift through the galaxy, vast regions where new stars are born from collapsing gas and dust. If our solar system collided with a massive nebula, the effects would be catastrophic. The dense gas would compress our heliosphere, potentially collapsing it entirely. Earth would be bombarded with cosmic rays at levels nothing evolved to handle. The nebula's dust and gas would block sunlight, plunging us into darkness. The drag from the nebula would slow Earth's orbital velocity, causing us to spiral toward the sun. We'd either freeze in the dark or burn as our orbit decayed, and either way, extinction comes from flying through a cloud of gas we never saw as a threat. Nebulae are massive, sometimes hundreds of light years across. They're diffuse, much less dense than Earth's atmosphere, but they're not empty. If our solar system entered a dense region of a nebula, the outer layers of our heliosphere would encounter resistance. The solar wind pushes outward against the interstellar medium, creating a protective bubble. But if that medium suddenly becomes thousands of times denser as we enter a nebula, the pressure balance shifts. The heliosphere would be compressed inward, potentially shrinking to within Earth's orbit. Without the heliosphere's protection, galactic cosmic rays would flood the inner solar system. Earth's atmosphere would be bombarded with high-energy particles. The ozone layer would be destroyed within years. Surface radiation would spike to lethal levels. Plants would die from radiation damage. Animals would develop cancers and mutations. The food chain would collapse as primary producers failed under the radiation assault. But the radiation might not be the worst part. Nebulae block light. They're dark because the dust absorbs and scatters starlight. If Earth entered a particularly dense region, sunlight reaching us would decrease dramatically. The dust wouldn't block all light, but even a 50% reduction would trigger a severe ice age. Temperatures would plummet, the oceans would start to freeze, photosynthesis would struggle with reduced light. The planet would cool rapidly as the nebula's dust created a barrier between us and the sun. The drag effect would be the final nail in the coffin. Earth moving through the nebula's gas would experience atmospheric drag, just like a satellite in Earth's atmosphere. This drag would slow our orbital velocity. As we slowed, we'd begin to spiral inward toward the sun. The process would take thousands of years, but it would be relentless. Earth's orbit would decay. We'd move closer to the sun, even as the nebula blocked the sun's light. Eventually, we'd get close enough that the increased solar radiation overpowered the blocking effect. The planet would heat, the oceans would boil. We'd be cooked in the sun's embrace, our orbit having decayed from the drag of passing through a nebula that took thousands of years to traverse but ultimately proved fatal. The probability of this happening depends on the sun's future path through the galaxy. We know of nearby nebulae. The closest is the California Nebula, about 1,000 light-years away, too far to threaten us. But the galaxy contains thousands of nebulae, and the sun's orbit will take us through different regions over millions of years. We might eventually encounter one. And when we do, we'll discover that even something as seemingly harmless as a cloud of gas can kill an entire world if the cloud is big enough and we're unlucky enough to fly through it at the wrong time. Quantum vacuum instability cascade, quantum field theory describes reality as fields permeating space, with particles as excitations of those fields. If multiple quantum fields are metastable, a cascade failure could occur where one field's transition triggers others. The Higgs field might decay, triggering electromagnetic field changes, which trigger changes in other fields. This cascade would rewrite all of physics simultaneously. The speed of light might change. Fundamental forces might have different strengths. Matter would be unable to exist in any stable form. The universe would be transformed into something utterly alien, and Earth would be destroyed in the first microseconds as everything we're made of ceases to follow the rules that allow atoms to exist. This is speculative physics at its most terrifying. We don't fully understand the quantum fields that make up reality. We've identified several: the electromagnetic field, the quark fields, the Higgs field, others. We measure their properties and build theories around them. But we don't know if these fields are in their absolute lowest energy states, or if they're metastable, temporarily stable, but capable of transitioning to lower energy configurations. If multiple fields are metastable, and if their energy states are coupled, meaning one field's transition affects others, then a cascade becomes possible. Imagine the Higgs field undergoes vacuum decay, transitioning to a lower energy state. This changes how particles acquire mass, but this transition might also affect the electromagnetic field's energy state because the fields interact. If the electromagnetic field is also metastable, the Higgs transition might trigger its decay. Now you have two fields transitioning simultaneously, but these two might be coupled to other fields. The cascade spreads. Within microseconds, every quantum field in the affected region would transition to new energy states. The physics would be completely different. Fundamental constants would have new values. The speed of light might be different. The strength of electromagnetic force might change. The strong nuclear force that holds atomic nuclei together might weaken or strengthen drastically. In the new physics regime, atoms couldn't exist. The electron-proton attraction might be too weak to form stable atoms, or too strong, causing electrons to collapse into nuclei. Chemical bonds wouldn't work. Molecules would be impossible. Even if some exotic form of matter could exist in the new physics, it wouldn't be the matter we're made of. Earth would disintegrate instantly. The atoms making up the planet would cease to be stable. They'd decay, transform, or simply cease to exist as coherent structures. The planet would dissolve into whatever exotic particles or energy configurations are stable in the new field states. Nothing survives. No atoms means no molecules, means no chemistry, means no life, means no anything. Just a region of space where the rules changed and everything that depended on the old rules was destroyed. The cascade would expand at the speed of light, consuming the solar system, then the galaxy, then eventually the entire universe. Behind the expanding wavefront, new physics. Ahead of it, the old physics we know. And at the front, the transition zone where everything is being destroyed and recreated according to rules that don't allow for the existence of anything we'd recognize. This is pure speculation. We have no evidence that quantum fields are coupled in ways that allow cascades. We don't even know for certain that any fields are metastable. But the possibility exists in our theories, lurking in the mathematics that describes reality's fundamental structure. And if it's possible, it might be inevitable given enough time. The universe might destroy itself through quantum cascade, rewriting the rules of physics everywhere, rendering itself unable to support complexity, structure, or anything that could be called existence in any meaningful sense. Intergalactic void passage. The universe isn't uniformly distributed. Galaxies cluster into filaments and walls surrounding vast empty regions called voids, some hundreds of millions of light-years across. If our galaxy's motion carried us into a void, we'd be isolated from the cosmic web structure. This isolation would have subtle but potentially deadly effects. The matter density would drop. Dark matter density would decrease. The expansion of space might behave differently in voids. Over hundreds of millions of years, our galaxy might be stretched, distorted, or torn apart by the different expansion dynamics inside a void versus the denser regions we currently inhabit. Earth wouldn't survive our galaxy's dissolution. Cosmic voids are mysterious. They're not completely empty, but they contain far fewer galaxies than the filaments and walls. The matter density is perhaps 10 to 20% of the cosmic average. Dark matter, which makes up most of the universe's mass, is also less dense in voids. This creates regions where gravity is weaker, and the expansion of space might proceed differently. Recent observations suggest space might expand faster in voids than in denser regions. This makes intuitive sense. Less matter means less gravity to resist expansion. If our galaxy entered a void, we'd transition from a relatively dense environment to a sparse one. The gravitational influence of nearby galaxies would weaken as those galaxies recede faster in the void's enhanced expansion. Our galaxy, the Milky Way, might begin to experience tidal forces from the differential expansion. Parts of the galaxy farther from the void's center might experience different expansion rates than parts closer to the center. This would stretch the galaxy over hundreds of millions of years. Stars would be pulled from their orbits. The galactic disk would distort. Spiral arms would unravel. Eventually, the galaxy might dissolve entirely, its stars scattered across the void as the structure holding them together is overcome by the enhanced expansion of space in the low-density environment. For Earth specifically, the timeline would be long, but the outcome certain. As the galaxy dissolved, our sun would be scattered. It might end up isolated in the void, far from any other stars, alone in a vast, empty region of space. Earth would still orbit the sun, but we'd be in a galaxy less void, the night sky nearly empty except for the faint glow of distant galaxy clusters hundreds of millions of light-years away. The isolation wouldn't directly kill us, but it would change the cosmic environment. Cosmic ray sources would be farther away. The interstellar medium would be nearly absent. The sun would drift through emptiness for billions of years until it died, taking Earth with it. But there might be more direct dangers. If the expansion of space within voids is significantly enhanced, it might eventually overcome the gravity holding the solar system together. Earth's orbit would expand. We'd drift away from the sun slowly, over millions of years, freezing as the distance increased and solar heat decreased. The void would pull us apart gently but inexorably, its enhanced expansion prying Earth from the sun until we were a frozen rock orbiting nothing in the middle of vast emptiness. This is a very long-term speculative threat. Galaxies don't move into voids quickly. The timescales are hundreds of millions to billions of years. But it represents another way the universe's large-scale structure could kill us. Not through violent events, but through slow isolation and dissolution in the vast empty regions that make up most of the universe's volume. Baryonic acoustic oscillation disruption, the universe's large-scale structure, shows patterns from sound waves that propagated through the early universe. These baryonic acoustic oscillations are imprinted on the distribution of galaxies. But what if those oscillations weren't entirely static? What if some mechanism could trigger new oscillations or resonate with the old patterns? A large-scale disturbance in the fabric of space-time, perhaps from colliding galaxy clusters or exotic cosmological events, could set up acoustic waves in the cosmic web. If these waves reached our region of space, they would compress and expand space itself in oscillating patterns. Earth would be subjected to gravitational waves at cosmological scales, potentially tearing apart the solar system through resonant effects we can't predict or defend against. This is highly speculative cosmology. Baryonic acoustic oscillations are well observed in the galaxy distribution, but they're frozen patterns from the early universe, not active waves. The idea that new oscillations could be triggered and propagate through the cosmic web is not part of standard cosmology. But physics allows for possibilities we haven't observed. If enough energy were released into the cosmic web structure, if colliding galaxy clusters or other massive events could disturb the web's geometry, waves might propagate. These wouldn't be like ordinary sound waves in air. They'd be oscillations in space-time itself, regions where space alternately compresses and expands in rhythmic patterns. If such a wave passed through our solar system, the effects would depend on its amplitude and frequency. A gentle wave might cause slight variations in gravitational forces, barely noticeable. A strong wave would create oscillating tidal forces. Earth would be stretched and compressed rhythmically as the wave passed. If the frequency resonated with any natural frequency of Earth's structure or orbit, the effects could amplify catastrophically. The planet might be torn apart by resonant tidal forces, or our orbit might be destabilized, thrown into chaos by the oscillating gravitational environment. The wave would pass in some period of time, maybe days, maybe years, depending on its wavelength. After it passed, the solar system would be left in whatever state the oscillations had created. Planets might survive, but with altered orbits. or the system might be shattered, planets scattered or destroyed, the sun left with a debris field where a stable planetary system once existed. We have no evidence such waves exist or could exist. This is speculation about physics at cosmic scales we don't fully understand. But the universe is large and old. Events we can't imagine might be possible. Disturbances we can't predict might propagate through the cosmic structure. And if one of those disturbances reached us, we'd face extinction from a cause so exotic that we wouldn't even have vocabulary to properly describe what killed us. Just that space itself oscillated, and in those oscillations, our world was destroyed. Photon underproduction crisis. Stars produce light through nuclear fusion. The sun converts mass to energy, and that energy eventually escapes as photons. But what if some process could interfere with photon production or cause photons to decay or be absorbed before reaching Earth? This sounds impossible given our understanding of physics, but exotic dark matter interactions or changes in fundamental constants could potentially affect photon propagation. If photons from the sun stopped reaching Earth in sufficient quantities, we'd freeze. The sun might still be fusing hydrogen, still releasing energy, but if that energy couldn't reach us as light, we'd die in the darkness and cold. This requires physics we don't currently understand, but it represents a category of extinction threat where fundamental processes we take for granted, like photons traveling from the sun to Earth, are disrupted. Photons are stable particles in standard physics. Once created, they persist until absorbed. They don't decay. They travel at light speed through space without losing energy unless they interact with matter or are redshifted by cosmic expansion. This stability is fundamental to how the universe works. We depend on photons behaving predictably. But what if dark matter, which we don't understand, could interact with photons in ways we haven't detected? Most dark matter models assume dark matter doesn't interact with photons at all, which is why it's dark. But suppose there's a form of dark matter that very weakly absorbs photons. Normally, this wouldn't matter because dark matter is diffuse. But if dark matter could clump or condense into regions of higher density, perhaps between the sun and Earth, it might absorb enough photons to significantly reduce the light reaching us. The process would be gradual. First, the sun would seem slightly dimmer. Scientists would puzzle over this. Is the sun changing? Are our instruments failing? Then it would get darker. The climate would cool. Crops would fail as photosynthesis declined. Ice ages would begin. We'd try to compensate with artificial light and heat, but we can't replace the sun's energy on a planetary scale. Temperatures would plummet. The planet would freeze as less and less solar energy reached the surface. Eventually, we'd realize that photons from the sun are being absorbed or deflected by something between us and our star, something invisible that's blocking the light we need to survive. But what could we do? We can't clear dark matter from space. We can't move the planet. We'd just watch helplessly as the sun dimmed in our sky, its light stolen by something we can't see or fight, until the planet froze and all life died in the cold darkness of a world orbiting a star whose light no longer reaches us. This scenario requires new physics. Photons don't behave this way in our current understanding. But our understanding is incomplete. Dark matter remains mysterious. Fundamental constants might not be constant. If some exotic process could interfere with photon propagation or production, we'd face extinction from the loss of light itself, dying in darkness not because the sun stopped shining, but because something stole the light before it could reach us and warm the world that needs it to survive. Spin-orbit resonance locking. Earth's rotation is gradually slowing due to tidal forces from the moon. Eventually, in billions of years, Earth would become tidally locked with the moon, one face always pointing toward it. But what if some event accelerated this process or caused Earth to lock with the sun instead? A massive asteroid impact, a close encounter with another planet, or a period of extreme tidal stress could alter Earth's rotation dramatically. If Earth became tidally locked with the sun, one hemisphere would face eternal day, scorching under constant sunlight, while the other would face eternal night, freezing in perpetual darkness. The habitable zone would be a narrow twilight band between the two extremes, and most of Earth's surface would become uninhabitable. The ecosystem collapse would drive humanity toward extinction. Tidal locking occurs when tidal forces synchronize an object's rotation period with its orbital period. The moon is tidally locked with Earth, which is why we always see the same face. Earth is not currently locked with anything, but the moon's tidal forces are slowing our rotation. Each day gets microscopically longer. In billions of years, if the sun doesn't destroy Earth first, we'd become locked with the moon. But external events could accelerate rotational changes. A massive impact could alter Earth's rotation rate or axis. If the impact transferred enough angular momentum, it might slow Earth's rotation significantly. A large enough impact might even stop the rotation entirely or reverse it. If Earth stopped rotating relative to the sun, we'd become tidally locked with one face always sunlit. The day side would be a scorching desert. With constant sunlight and no night to cool down, temperatures would climb to extremes. The oceans would evaporate on the day side. The atmosphere would be driven toward the night side by the temperature gradient. The night side would be a frozen wasteland. With no sunlight ever reaching it, temperatures would plummet to extremes. The atmosphere and oceans would freeze and accumulate on the night side. Between these extremes, a narrow twilight zone would exist where temperatures might be moderate. This band would be the only habitable region, a ring around the planet where the sun sits perpetually on the horizon. This region might support life, but it would be a fraction of Earth's surface. Most of the planet would be uninhabitable, either too hot or too cold. The atmospheric circulation would be catastrophic. Hot air from the day side would rush toward the cold night side, creating perpetual hurricane-force winds in the twilight zone. The weather would be violent and unpredictable. The ecosystem would collapse as the vast majority of Earth's surface became uninhabitable. Billions would die as habitable land vanished. The survivors would cling to the twilight zone, but even there, the extreme weather and limited resources would make long-term survival questionable. This scenario is unlikely in the near term. Tidal locking takes billions of years under normal conditions, and even a massive impact probably wouldn't cause immediate locking. But it represents another way Earth's rotation, something we take for granted, could be disrupted with catastrophic consequences for habitability and survival. Strange quark star formation. Inside neutron stars, the pressure is so extreme that quarks might not remain confined in protons and neutrons. They might collapse into a quark-gluon plasma or even more exotic quark matter. If our sun, under some extreme condition, collapsed not just into a neutron star but into a quark star, the energy released would be beyond imagination. But we don't need the sun to do this for extinction. If a nearby quark star formed from another stellar corpse, its radiation and particle emissions could threaten Earth. Quark stars might be even denser than neutron stars, with magnetic fields and rotation that make them deadlier than pulsars. One forming within a few light years could bathe Earth in lethal radiation we'd have no defense against. Quark stars are theoretical stellar objects where the neutron star's matter has collapsed into deconfined quarks. In normal matter, quarks are confined inside protons and neutrons by the strong force, but at extreme pressures and densities, this confinement might break down. The quarks would form a soup, a quark-gluon plasma, or potentially strange quark matter if enough strange quarks are produced. A quark star would be smaller and denser than a neutron star of the same mass. It might only be 10 kilometers across instead of 20. Its surface gravity would be even more extreme, and its magnetic field might be stronger, potentially reaching magnetar levels or beyond. The formation of a quark star from a neutron star would release enormous energy as the matter rearranges into a denser configuration. If this happened nearby, within a few hundred light years, the burst of energy and radiation could be detected on Earth. If it happened very close, within 10 or 20 light years, the radiation might be dangerous. The energy release would include X-rays, gamma rays, and possibly exotic particles we don't normally encounter. Earth would be bombarded with high-energy radiation. The ozone layer would be damaged or destroyed. Surface life would be exposed to lethal radiation levels. Even if the quark star formation event itself was brief, the resulting object might be dangerous long-term. A quark star with magnetar-level magnetic fields would emit intense radiation and particles. If it was a pulsar, its beam would sweep through space. If Earth was in the path of that beam, we'd be irradiated periodically. The cumulative radiation dose over years could cause ecological collapse, mass extinctions, and the end of human civilization. The probability of a nearby quark star formation is very low. Most neutron stars probably don't collapse into quark stars, or if they do, it happens in the first moments after their formation, not later. And there aren't many neutron stars close to us. But in a galaxy with billions of stars and likely millions of neutron stars, exotic events happen somewhere. If one happens too close to us, we'd learn that the universe has ways to kill us that we barely understand. Exotic physics playing out in stellar corpses whose very existence challenges our theories, and whose radiation can reach across light years to extinguish life on worlds that never even knew such objects existed until their deadly light arrived.